your name, and you were going to give us a background or something, right?
Okay, my name is Thomas Paniculangara. I'm from the business school, marketing. I usually teach market research, which is a quantitative. I teach it as a quantitative subject, although it can be done as a qualitative subject. And as I read through a lot of the theory in my area, I realized that we don't have an undergraduate course in this area, and it's something that is very interesting. So this is my course on which I'm planning to design and decision making for consumers. And I'd like to start off right now. I'm just going to get rid of this chair because I don't really need it and I like to move around. So right now we're into the third week of the third class of our course. And in the first session I talked to you about the syllabus, the objectives of the course, and I'd just like to remind you about what it is. There is a difference between the normative, that is what is right, and I'm just going to write down those two words just to remind you. Norm, that is what is right, and descriptive, that is what actually happens in some sense. So just to give you an example of the two types of theories, in normative we usually talk about what is right, so it draws a lot from theory in economics, expected utility theory by von Neumann and Morgenstern. Descriptive is something like prospect theory, which we talk about in terms of an example is Kahneman and Tversky. They came out with prospect theory. Today, so what I'm going to do is we're trying to contrast the descriptive and the normatives in this course. So I'll teach you what is normative, and I'll also tell you the theory about how people do not follow the normative way of doing things. But first, in order to understand the normative, we've got to understand information that is presented to us in the world. Part of that is, some of the information we get is probabilities. So how do you make sense of probabilities? How do people make sense of information presented to them in the form of percentages, etc.? So and I'll probably also talk to you about something which is new, which is a lot of medical tests, a lot of other tests that we do may be false. So how much should you worry if you test positive for, let's say, a condition? I'd like to introduce a couple of terms here. Sensitivity, the correct positive rate. Now, the people who go for a test, let's say they are divided into good and bad. Bad means people who don't have it. Good means bad means people who have it. Good means people who don't have it. The sensitivity is, out of the people who have it, or who are bad in some way, how many are correctly identified? Sensitive, how sensitive is the test, in other words. Specificity is this test able to separate the two kinds of people? Is it able to separate the good and the bad people? There is a possibility that the people who don't have it, the good people, may be labeled inadvertently as bad people. They may have it. So the specificity, specific, is how easily can the test separate the two. And here, base rate is something that it's used in, you can call it incidence rate, you can call it a whole number of things, but it is as the population, or the entire population, how many of them are actually positive or how many of them are bad. So those are the three terms that we need to work with today, and which is used in a lot of medical literature. There are differences, and you will see those differences. Sometimes sensitivity is called correct positive rate, that is positive positive. Sometimes specificity is called negative negative. Different terms across different continents. So you may see these terms used in different ways. Now, as an exercise today, I'd like you to consider a test for a disease that the disease has a 1% base rate. That is, in the people who take the test, 1% of them will come out, 1% of them are actually bad, actually do have it. 95% sensitivity, that is, out of the people who have it, 95% of them will be correctly identified. 99% specificity, out of the people who don't have it, 99% will be correctly identified as not having it. So let's start with this, and instead of looking at percentages and probabilities, let's instead work with numbers. We're human beings. We think of numbers of people. We think of actual people. So let's start off with 1,000 people. Just grab a number which is easy to work with. Now with those figures, how many of these 1,000 people do you think will actually have the disease? I need some help here. Anyone?
100?
There's a 1% base rate. So how many of them will have it?
1%?
1%. 1% of 1,000 is 10. And I plan to use red. I didn't plan to use blue. Red seemed more thing. So there'll be 10 people who will have the disease, and there'll be how many are left over who won't have it? 990 don't have it. And let's label this as let's call it that and this. Now, with 95% sensitivity and 99% specificity, out of the 10 people, how many do you think are going to be correctly identified by this test with 95% sensitivity? That is, it'll identify 9.5, right? That is, and let's change colors here. 9.5 will be correctly identified as positive, and we're going to leave the fractions the way they are. 0.5, although it doesn't make sense, I know, to have half a person, but for this demonstration, yes. Now, with 99% specificity, how many people out of the 990 are going to be incorrectly identified as having the disease? So 99% of them, what is 99% means 1%, that is 1 minus 0.99 is going to be 1% of them are going to be incorrectly identified. So what's 1% of this? Okay, so 9.9 people are going to be positively identified, and the rest of them, whatever that may be, so 990 minus that will be 980.1, right? Correct me if I'm wrong. So that will be negative. Now, so you have 9.5 people as positive, who are positive, 9.9 people who are actually negative, who have been incorrectly identified as positive. What is the conditional probability if you've been given a positive result that you actually have the disease? So you think of the number of people who have it, which is 9.5 plus 9.9, and what will go on top? The number of people who have it. How many are the number of people who have it? 9.5, right? So that's 9.5 divided by 9.5 plus 9.9, and that will give us 9.5, and this is 18 plus 1.4, I believe, so 19.4, right? And that should be, and those of you who have a calculator can do it, I calculated ahead of time, it's about 46%. Is it a good test? It's not a good test, right? The problem is that 46% of the people who test positive, only about 46% of them are actually positive. It's not a good test. But more to the point in the class that I'm planning to teach is that people aren't taught to imagine the number of people, 1,000 people. Instead, they are taught, that is a question that I was planning to ask, but people are taught this Bayes rule of conditional probability. Does that make sense? Do you remember this from your earlier classes?
Oh, yes.
Yeah. So let's try and apply Bayes rule, okay? Just so that we get the same thing. Bayes rule is probability of B given A. That is, A is the probability of a disease. That's 0.01, 1%. Probability of not having a disease is 1 minus 0.01. That's 99%. Positive result is the sensitivity, which is 95%. Probability A is equal to 0.01. Probability A not happening is 0.99. Those are all the numbers you need, and positive result. So that is going to give you 0.95 times 0.01 divided by 0.95 times 0.01. Remember, it's probability of B given A times probability of A. Same thing at the bottom, plus probability of B not, that is the probability of a positive result given that you don't have it. That's 0.99 sensitivity times 0.01. Okay? Right? Probability of B given A given C. Okay, it's 0.01 times 0.99 because 99% of people don't have it.